Now, the student of class 12, today I'll also continue with the second order derivative, some important questions. Now, today is the last class of second order derivative. Now, given quantity is since y is equals to sine of m sine inverse x, prove that 1 minus x square y2 minus xy1 plus m square y equals to 0. This you have to prove. Now, first of all, that you have to calculate the first order derivative, differentiating with respect to x, dy upon dx. So instead of writing dy by dx, the given notation is in terms of y1 and y2. So I'll write the first order derivative is y1. Derivative sign is cos of m sine inverse x into m. Derivative of sine inverse x is 1 by under root 1 minus x square. Now it is in terms of numerator over denominator form. Last video only we did these things. Now cross multiply, then we'll get 1 minus x square into y1 is equals to m cos m sine inverse x. Again, differentiating with respect to x. Now then we'll use u into v formula, product from u dy dx of v plus v dy dx of u x square equals to m into, now the derivative of this quantity, derivative cos is minus sine of m sine inverse x into m. Again the derivative of sine inverse x is 1 by under root 1 minus x square. Now then under root 1 minus x square, dy dx of y1 is y2 plus y1, and derivative of root, it is 1 over 2 under root 1 minus x square into the derivative 1 is 0 minus 2x equals to m into m squared will be minus m square sine of m sine inverse x divided by under root 1 minus x square. Now after this, now what you have to do is under root 1 minus x square y2 minus into plus minus 2x y1 over 2 under root 1 minus x square equals to minus m square. In previous section that you have to prove y. That means sine of m sine inverse x. Sine of m sine inverse x is y. And so in place of this function we can write y over under root 1 minus x square. Now these two quantities get cancelled. Now that I'll do over here. Now from this continue. Now say if you cross multiply these things, now say if you multiply this quantity, under root 1 minus x square into under root 1 minus x square will be 1 minus x square y2 minus, and if you multiply this quantity, this will come over here, this and this get cancelled, then what remain over here? X y1 is equals to minus m square y. Now then bring this in this quantity, it will be 1 minus x square y2 minus x y1 plus m square y is equals to 0. It is proved. Now another question. The given question is y is equals to a cos of log x plus b sine of log x, so that x square d2y by dx square plus x dy by dx plus y equals to 0. Now since y is equals to a cos log x plus b sine log x, now differentiating with respect to x. Now in this question it is dy by dx is given, so I'll write dy by dx equals to a, and derivative cos is minus sine log x into the derivative log x is 1 over x plus b, derivative sign is cos of log x and derivative log x is 1 by x. Now dy by dx, now then I'll take x LCM. If I take x LCM, then we have a sine of log x plus b cos of log x. Now it is also in terms of numerator over denominator form. Numerator over denominator. What you have to do next is cross multiply, then Find the second order derivative. X dy by dx equals to minus a sine of log x plus b cos of log x. Now then we'll use the product formula. Now then I'll use u into v. U d by dx of v, that is dy over dx, plus u d by dx of v plus v d by dx of u equals to, now then again that you have to differentiate this quantity, minus a, derivative sign is cos of log x, and derivative log x is 1 over x, plus b into derivative cos is minus sine of log x into derivative log x is 1 over x. X into dy by dx of dy by dx is d2y by dx square plus dy by dx into derivative x is 1 equals to, again over here in the right hand side we have x LCM. If I take x LCM, now this one will be a cos log x minus b sine log x, and then I'll cross multiply. I'll write these things over here, the proving section. Now then I'll cross multiply this quantity. It will be x square d2y by dx square plus x dy by dx equals to, now right hand side after the cross multiplication, now we have minus a cos log x minus b sin log x. Now then I'll take minus common from the right hand side. If I take minus common, this one will be a cos of log x plus b sin of log x. Now x square d2y by dx square plus x dy upon dx equals to minus, and this whole quantity within a square bracket quantity is equals to y. A cos log x plus b sin log x equals to how much? A cos log x plus b sin log x equals to y. Then instead of this I'll write y. If you bring this y, then you'll get the proving. Plus y equals to 0. Now another question. Log y is equals to tan inverse x. Prove that 1 plus x square y2 plus 2x minus 1 y1 equals to 0. Now since log y is equals to tan inverse of x, now I'll differentiate this function. Differentiating with respect to x, derivative log y is 1 over y into the derivative of y with respect to x is y1. Actually it is dy by dx. Instead of writing dy by dx we can write y1, because in proving section y1 and y2 is given. Okay, now the derivative of tan inverse x is 1 by 1 plus x square. Now then I'll cross multiply these things. It will be 1 plus x square into y1 is equals to y. Again differentiating with respect to x, u into v formula, 1 plus x square d by dx of y1 plus y1 d by dx of 1 plus x square. Again the derivative of y1 will write y is y1. Now 1 plus x square d by dx of y1 is y2 plus y1 into derivative 1 0 plus 2x is equals to y1. Now it is 1 plus x square into y2 plus 2x y1 is equals to y1. But the proving is a little bit different over here. Now to prove this identity, I'll bring this y1 from left hand side to the right hand side to the left hand side. So 1 plus x square plus 2x y1 minus y1 equals to 0. Now this identity is proved. Now dear student of class 12, now this finished, I have finished inverse trigonometric function and the first order derivative and the second order derivative. I'm not going to do continuously with the application of derivative. Now from the next video I'll start integral calculus, and that one is very important. Okay, thank you this much for today. Thank you. Next video will be of integral calculus.